Okay, welcome back. This is Mr. Hassan's Maths channel. I'm now answering question number 7 from the October 2024 Pure Mathematics P4 paper from the International A-Level Edexcel Examining Board. And here we've got a question where they've told us figure 4 shows a sketch of part of the curve with the equation y equals 3x minus 1 over x plus 2, where x is greater than negative 2. We've got to show that 3x minus 1 over x plus 2 is identical to a plus b over x plus 2, where a and b are constants to be found. Now there's numerous ways that we can answer this question. I'm going to show you 3 ways of doing it. First way, the way I prefer for a simple question like this is called rewriting the numerator. So I leave the denominator as it is, x plus 2. And I write x plus 2 in the numerator exactly as it is. Then I ask myself, how does this x plus 2 end up being 3x minus 1? Now multiples like this have to be given by multiplication, not by adding like another 2x, for example. So I want to multiply this by 3. That's where I'll get my 3x. Now multiply it by 3, I get 3x plus 6. But I want to end up with negative 1. So if I got 3x plus 6. What do I have to do to end up with negative 1? Well, I have to take away 7. So I've got to take away 7 from this. Now what we have here is this fraction. We can split it up into 2 separate fractions. So we have 3 times x plus 2 over x plus 2 minus 7 over x plus 2. And here we have a common factor of x plus 2. We can cancel them out. So that gives us 3 minus 7 over x plus 2. So that's one way of answering the question. It's called rewriting the numerator. So you write the denominator, you copy the denominator into the numerator, and then you kind of adjust it so that you end up with something where you have that denominator written as it is, but you write things around it such that you end up with your fraction. The second way is probably the most popular way, is by algebraic long division. So you have x plus 2 and you got into 3x minus 1. Say, okay, x times something gives, what am I doing? Into 3x minus 1. So x into 3x goes 3 times. 3 times 3x plus 2 gives you 3x plus 6. You have minus 1, take away 6, which is minus 7. There's nothing left to bring down. So we have this as the quotient and this as the quotient, and this is the remainder. So we can say that 3x minus 1 over x plus 2 is identical to, you have the quotient, which is 3, and the remainder, which is minus 7. So you have minus 7 over the original denominator, which is x plus 2. Okay, so that's using long division. And a third way we can do this is by what's called comparing coefficients. So we start off with 3x minus 1. 3x minus 1 over x plus 2 is equivalent, which is identical to, a plus b over x plus 2. So what I'm going to do is I'm going to multiply both sides by x plus 2. Okay, so I end up with 3x minus 1 equals a times x plus 2 plus b. Alternatively, I can think of it is I make this into one fraction, and then the denominators are the same, therefore the numerators will be the same. If I make it into one fraction, I'll end up with this. I have to put this over x plus 2, so I have a x plus 2 over x plus 2 plus b over x plus 2. So now we see that the numerators have to be the same because the denominators are the same. So these are the same as each other. All right, so we can equate them. Now these are identical to each other. So now we can compare the coefficients, or we can, even do substitution, whatever, to find out what we need. If you compare the coefficients, probably easier. The x coefficient on this side is 3, and on this side the only x term will be ax. With no other x term. So a is equal to 3, and we can also compare the constants. With the constants we have here on this side, we have -1, and on this side we have 2a plus b. 2a plus b. 2a plus b. And we know a is 3, so you have minus 1 equals 2 times 3 plus, we know a is 3, sorry, so you have minus 1 equals 2 times 3 plus b. So minus 1 equals 6 plus b. So b is equal to negative 7. So we end up with 3x minus 1 over x plus 2 is equal to 3 minus 7 over x plus 2. So whichever way you want to use is perfectly fine. I personally, in simple examples, I like to use the first method. If it's a bit more complicated, I would use the second method. The third method is something which we have to get used to in certain cases of partial fractions, which we're going to deal with probably in other questions. But we have to have some understanding of this method for P4. But for this particular question, any of these three methods would be perfectly fine. So we end up with 3 minus 7 over x plus 2. Okay, that's part A. And then part B, it says the finite region R, shown shaded in figure 4, is bounded by the curve, the line with the equation x equals 4 and the x-axis, and the line with x equals 1. The region is rotated 2 pi radians about the x-axis to form a solid of revolution. Use the answer to part A and algebraic integration to find the exact volume of the solid generated. Give your answer in this form. So let me just get this ready. Okay, now for part B of this question. It says the finite region R, shown shaded in figure 4, is bounded by the curve, the line with equation x equals 4, and the x-axis, and the line with x equals 1. The region is rotated through 2 pi radians about the x-axis to form a solid of revolution. Use the answer to part A and algebraic integration to find the exact volume of the solid generated, giving your answer in the form pi times p plus q ln 2, where p and q are rational constants. So they most probably end up as being fractions. Okay, now, to find the volume of revolution of a solid, I've explained this in quite a few different videos already, but basically this solid is going to be rotated around the x-axis. Okay, so it looks something like this. Okay, so basically it's going to become three-dimensional. It's going to come out of the page and back into the page. Something like this, not that well drawn. So you'll end up with basically a curvy kind of edge cone type of shape, right? Truncated at the top. So that's what's going to happen here between these 2 points. Okay, now how do we find the volume of revolution? Well, we know there's a formula that we can memorize. The volume is pi times the integral of y squared dx between the limits of a and b. Okay, we can put a and b this way if you want to. If this is b, this is a. All right, that will give you the volume of this solid as it revolves around the x-axis, going through 2 pi 1 whole revolution. That's called the volume of revolution of the solid. All right, so now, where does this formula come from? You can just memorize it if you want to, no problem. There's absolutely no reason for you to know where it comes from. But I like my students to have some idea of where things do come from. And basically what it is, it's derived from the formula of a cylinder. The volume of a cylinder is pi r squared h. And the reason why we have this cylinder is because what we have here is, I should have used that from the beginning for this as well. Anyway, no problem. Okay, what we have here is, just say this is a small slice of the shape as it's revolved around the x-axis. And we have here, from that point to that point would be the radius. That would be the radius of this cylinder. Okay, that would be the radius of the cylinder. So we have a cylinder that's like this. Do they in fact have cylinders here? Do they have 3D shapes here? I'm not sure. I'm sure they did. Oh, they don't. Okay, no problem. So we have our cylinder. Okay. Copy first and then paste. All right. So we have our cylinder, which is quite thin. Okay, very thin cylinder. So thin that the thickness, we call it just a small part of x, we call it dx. The radius of the cylinder, as we said, is y. So the volume of the cylinder is pi times the radius, which is y squared, times how deep it is, which is dx. Okay, so what we want to do is we want to find the sum of all the cylinders from A to B, find the sum of all of them. And that's what the integral sign actually originally means. It means the sum of. So we're finding the sum of all of the cylinders from here to there. A to B, we're adding all those volumes of those cylinders together. Okay, and that's how we get the volume of the solid. So that's where the formula comes from. So we know that y equals in the form that they told us to use, 7 minus, I'll write this as x plus 2 to the power of negative 1. Okay, and we've got to find the volume, which will be pi times the integral between the limits of 1 and 4 of this squared. So 3 minus 7x plus 2 to the power of minus 1. All of that has to be squared, pi y squared dx. Right, so we have to integrate what we have here. Now to integrate this, I need to expand this bracket, okay, which looks like a bit of hassle, but we'll do it. So we have pi times between 1 and 4. So if you square 3, you get 9. Right? And then we're going to have 3 times this term doubled. So 3 times 7 times this, that's 21, doubled is going to be minus 42 times x plus 2 to the power of negative 1. And then you're going to square this last term. If you square the last term, you're going to have plus 49. And if you do x plus 2 to the power of minus 1 and you square it, you multiply the power, so you'll have x plus 2 to the power of negative 2. Okay, and that needs to be integrated with respect to x. So now the terms are kind of ready to be integrated. This one I'm going to rewrite it because this is the type which is you can say the reverse chain rule for ln. We can use for that one because we can't add 1 to the power, you get 0, and you divide by 0, it doesn't work. But this one, because if you write it in this form as 42 over x plus 2, the numerator is of the form of the differential of the denominator, so we can reverse the chain rule for ln. This is like the result of the chain rule being used, okay, for ln of ln of x plus 2, some constant times ln of x plus 2. And this is going to be plus. This one is fine as it is because we can deal with this power. And you see, we can reverse the chain rule for this y because if you differentiate what's inside the function, you get what's outside the function. Well, you get a constant. You get a constant. Differentiate x plus 2, you get 1. Outside is 49, which is also constant. So this is of the form where you can have k times, you can say g dash of x multiplied by f of g of x. Meaning basically that you have a function inside a function, you differentiate that function, outside of that is multiplied the differential of that function, some constant times that. So you have x plus 2 to the power of negative 2. This is perfectly fine as it is. So we can now start to integrate these terms. So I'll put my square bracket now. 9 integrated with respect to x gives us 9x. As we mentioned, this is going to be minus 42 times the ln of the modulus of x plus 2 divided by 1. That's fine. And here we're going to have 49 times x plus 2 to the power of negative 1. Add 1 to the power. Divide by the new power and also by the differential what's inside the function, which is just 1. And we're almost ready now to start putting the values in. Let's just simplify this last thing a little bit. So that's going to be pi times 9x minus 42 times the ln of the modulus of x plus 2 minus 49 over x plus 2 between the limits of 4 and 1. And now we can start putting the values in, and hopefully we'll end up with something of this form. It looks like we will because we got the ln there. So we got pi. Don't forget the pi. Many people forget the pi in these questions. Don't forget the pi. So 9 times 4 minus 42 times the ln of 4 plus 2, which is 6. We don't put the modular sign once we know it's positive now. Minus 49 over 4 plus 2, which is 6. Okay, minus, and now we're going to put 1 instead of x. So you're going to have 9 times 1 minus 42 ln of 3. 1 plus 2 is 3. Minus 49 over 1 plus 2, which is 3. Okay, so this is going to give us, all of this is multiplied by pi, by the way. So you have pi times 4 9s are 36. Okay, minus 42 ln 6 minus 49 over 6 plus minus 9. Okay, so you got minus 9 plus 42 ln 3 plus 49 over 3. So let me just use the calculator to deal with the numbers. Okay, so we got here 36 minus 9. Then we got the fractions minus 49 over 6 and plus 49 over 3. Okay, so I've done 36, this, and this, 4 of them, okay. That gives us 211 over 6. So you have pi times 211 over 6. And now you've got these two to deal with. So I've got let me put plus 42 times, so I've got plus 42 ln 3 minus 42 ln 6. Let me write it that way. That'll be a bit easier. Okay, so you have 211 over 6. Don't forget the pi. And this I can take out 42 as a common factor. And I've got ln 3 minus ln 6. And I can use my, the laws of logarithms where I have ln 3 over 6. That's going to be ln over half. So you're going to have pi times 211 over 6, okay, plus 42 times the ln of 1 over 2. Okay, so now the answer has to have a ln 2 there. Okay, so what we can do is, we know that 1 over 2, we know that the ln of 1 over 2 is the same as the ln of 2 to the power of minus 1, which is minus ln 2. So I can write that as minus ln 2. So that'll be pi times 211 over 6 minus 42 ln 2. And hopefully that would be the correct answer. Okay, so there we have the answer to this question. And it says use to find the exact volume. So we can say units cubed. Not really necessary, but that makes it more complete. And there's the answer to question number 7, part B. And I think that was the end of question 7. That's right. So, sorry, that completes this question. I hope that was clear. Other questions from this particular paper can be found in the playlist that will appear in the top right of the screen at the end of this video. Other questions from the topic of volumes of revolution from P4, you can find that in this playlist over here. You'll find here a playlist which is dealing with just integration in general from P4. You can subscribe to my channel by clicking on the link at the top. Thank you for watching and see you soon.